Hello. Hi, Brendan.
Morning.
Okay. They're gonna be slow to come in, aren't they? Okay. Okay. Ah. Sorry. And I'm only in 108 and 111 in this one, so. But let me get my key and see.
So was it counted present or no? Because you know, I told you that I was doing the Zoom. Okay.
magic keys, I'll let you into any room in this building if you're in a system to be in that room. So I'm in the system to be in this room next door and 109 as well. I didn't realize that. So, yeah.
Was the one he needed?
Huh?
Is that the one he needed or no?
I couldn't get into it.
Oh,
He needed 130, and I think I can get a 132, but not 130. I'm doing something very quickly. I meant to do last night, but last night was not a good night for me. Okay. And I need to go to another class and do the same thing. There we go. If y'all look in your in Canvas and files in this course, there are in the folder called handouts, there's 2 more files. One's called trig formulas and the other one's trig identities. So there's like the trig identities, there's 55 problems there.
Can't hear.
Oh, damn it. You could hear me earlier. Why can't you hear me now?
I can hear you.
Okay. Not everybody can hear me then. Okay. Can you hear me? Can you hear me now? Or a phrase from Verizon.
Yeah, we can hear you.
Oh, yeah. Yeah. There are some people who cannot hear me. And so if you can't, you need to talk to me. So I need to find where we left off last time. The PowerPoint hasn't been cooperating with me and telling me where I leave off. And we got into law of signs. Or did I just get to that slide? Law of signs. Let me pull it up. So did I just pin my screen to everybody's Zoom? So I am front and center. Got to turn the projector on. Oh, it's been a rough couple of weeks for me. Just apologize for all the delays that I've had. Really had no good excuse for all the delays that have been going on, just that they've been happening. Oh. And I think can't hear you. Sounds like yeah. Strange things happen. Sebastian. If my middle child had seen that, where you said that was strange, he would point at you and yell, "You're strange." Okay. And he's infected, so. He's a good kid.
Professor,
Yes,
what were you saying about the handouts and the files?
there should be 2 new handouts in the files. Let me go to those. Well, let me pull up this. Let me pull up this class. Oh, is this showing? Is it showing on my? Is it sharing?
I just see the love signs.
Okay. Let me pull this back up and stop that. So I can go back here. I got out of our class in Canvas. I have to get back into it and pull up files. And let me magnify this a little bit. Okay. So now when I share a screen, maybe it'll show up there. Okay, here we go. You who be in the classroom can't see it because it doesn't go up here, it's over here.
Yeah, I saw it over here.
Okay, in Canvas for this course, under files, under handouts, here it is. There are 2 new items. And trig formulas, which did that show up on your screen? You have to tell me yea or nay because I can't.
Yes, we can see it.
Okay, so and notice under the Pythagorean formulas, it not only has the sine and the tangent, it's got for all of them. So, and then sum to product, product to sum, half angle, double angle, power reducing, that's what they call those, power reducing. And then sum and difference, and I think there's some other, aren't there? There's a double angle. Are there any missing from here? If there are, please. Let me know. And I will add them. Anyway. So the half angle, tangent of the half angle, has three formulas you can use, three versions of it you can use. So you're allowed to use this on the test, which is happening next Wednesday. So we're not going to be covering anything new today. Okay, because I think trig identities is enough for everything to be on the test, and then I need to see what we've done before we got into trig identities that will be on the test.
Are we
So
gonna
this.
Sorry.
Say again. I'm sorry.
Are we gonna have another review for the exam number 2?
Yeah.
Okay, cool.
And one thing that's going to help with the review is this other. Oops, there it is. There. Is this other trig identities here? You go here, and it looks like one big massive thing. Okay, so some of these we may have already done in class. I don't know. But there's 55 of them, trig identities to do. Okay. Oh, there's 57. I'm sorry. I remembered incorrectly. So cotangent to the third power of x. How do we show that it equals this? Okay. And then the answer sheet goes through one possible way of doing it. All right. Realizing in mathematics, there's not always just one set path to solve. Oh, you can't see me. One set path to solve anything. So they give you one way. And there might be some steps combined in doing this. So just be aware of that.
Excuse me, when is it due?
Say again?
When is it due?
Oh, is it due?
When is it?
Oh, this is part of the review to start looking at.
Oh, okay.
Okay, because the next test will have I think it's going to be primarily the trig identities.
All right.
Okay, I can't remember where we left off on the first exam at the moment, but there
And the
might.
test is gonna be the 27th, right?
Say again?
The test is gonna be the 27th.
Pretty much chapter 7. Yeah. Chapter 8. What was at the beginning of chapter 8?
I think she said on the 27th.
Oh, the 27th? Yes. Yeah, my old ears are having a hard time understanding you. I'm sorry. So mostly chapter 7, chapter 8, you'll see on the third exam, and whatever else we cover before that exam. And what else?
When will you have the review ready?
I'm gonna start working on it today and tomorrow. And so I'll hopefully have it ready for you all Friday or Saturday. But that worksheet is a good one to start with. And that's what I'll do today. I shall stop the share. And I shall shut that down. Oh, wow. There should be an infinite number of me in that picture now. Okay, yeah.
They're going away.
Yeah, I keep forgetting that either the computer resets my settings or someone after me resets my settings. So. There we go. What was that? Where's my Zoom? Oh, my Zoom screen got memonized. I have to be careful how I say memonized. Because I say it wrong. I've always pronounced it wrong. My wife has been on my case since before we got married to say it correctly. All right. Go all the way up. So from that trig identities worksheet number 1, it has cotangent times secant, cotangent times secant equals what? Cosecant? Cosecant. This is an easy one. Because we're going to write cotangent and secant in terms of sine and cosine. Cotangent is cosine over sine. What was that? What was it? And secant is 1 over cosine. Well, this works out nice because these disappear. Say again? Thought I heard someone. These go to 1, so they go away. So we have 1 over sine. And 1 over sine is cosecant. And so we're done. On the test, if you have this problem on the test, this is the work I expect to see. Right. Please be sure you're on mute. There we go. So I want to look at number 6. For those of you who have it pulled up. All right, if you look at that sheet of trig identities, when I was in high school and I took trig, when I was in high school, they didn't have pre-calculus per se. What they had was a semester of trig and then a semester of either analytical geometry or elementary analysis, which is what I took my senior year, but that's a different story. And my trig teacher, and most trig teachers at the time, allowed you to use a 3x5 index card, and you could use both sides and cram on there all the formulas you wanted on there. I was having so much fun with this stuff when I was in that class that those formulas just resided in my head. I didn't have to write them down. So I came in with a blank 3x5 index card where all my friends came in with, I mean, the front and back were so covered, you couldn't, it was hard to read it. Anyway, and that's what the worksheet is. Any of the trig identities that you would need to use on the test is on that formula sheet. So now I gotta, where I said number 6, right? Was it sine theta, tangent theta, cosine theta, plus minus cotangent theta, cosine theta. And we want this to equal to 1 minus cosine squared theta. Oh, 2 cosine theta. 2 cosine squared. That's from one of the formula sheets. One of the trig formulas. So is this a half angle of cosine? I mean, a double angle? Cosine 2 theta equals this. Am I correct? It's been I don't always remember. Now, there are several ways to attack this. Write everything in terms of sine and cosine. And I'll do that. Sine theta times sine theta over cosine theta times cosine theta minus cosine theta divided by sine theta times cosine theta. This cosine and this cosine go to 1. And so we have sine theta times sine theta minus cosine squared theta divided by sine theta. Okay, I just multiplied the cosine times the cosine to get the cosine squared. Now, the next thing I'm going to do, I'm going to multiply it in by sine. So sine times sine squared. I mean, sine times sine is sine squared theta. And then sine times cosine over sine theta. Well, the 2 sines will go away, and so that'll just leave me a minus cosine squared theta. Well, isn't this cosine of 2 theta?
Oh, yeah.
Yeah. So yeah, it's cosine of 2 theta. Which is 1 minus 2. No, that'd be 1 minus 2 sine theta. Oh, no, it isn't. it isn't. I was wondering about it because I thought the cosine came first. It does come first. So if I factor out a -1, that's going to be negative times cosine squared theta minus sine theta. If I factor out a -1, I just switch the order of the subtract. Now this is a minus the negative of cosine 2 theta, which is the negative of 2, I keep forgetting the 2 cosine squared theta minus 1. Well, now when I bring the minus sign inside, I get this. Am I still on the screen? Yes. Yeah, I'm still on the screen. So I'm gonna write it down here. So then so multiplying in by the negative, I'm gonna change the order of the subtract. So it's gonna be 1 minus 2 cosine squared theta, which is what we wanted to get. I wouldn't want too hard. I mean, I saw that this is the double angle formula, but I thought it was a little off because I thought the cosine went first, and then I realized it's just factoring out a -1, factoring out the negative. And so that's what we got. Questions?
So if we get a question like that, and like, we already know that it's like cosine. Like, we already know that it's like true, you know what I mean? Because you said like, oh, like you already know.
You know, this does equal this.
Yeah, like if you know,
Prove it.
oh, we have to prove it.
That's what all this work is doing, is showing that this expression here does in fact equal that.
Oh, okay.
That's all this is doing. It's like you're working a problem and you know X is 7. You're supposed to get 7, so we'll prove it. It's like when we were doing it's in my college algebra classes, sorry. When you were, if you remember from college algebra, where you were finding the zeros of a polynomial function, and you were using synthetic division to find out what the zero, to see if you get 0 from that number. Well, if you already know you're going to get 0, then you can do the synthetic division to get the depressed equation. So you can factor that, or do synthetic division with that. So you already knew you were going to get 0 at the end for the remainder. It's just, what are these numbers here?
Yeah.
So yeah.
I have a question.
Yeah.
Okay, so on the last line, you know how it says sine times sine minus cosine squared theta over, yeah. So what happened to the denominator?
Oh, here.
Yeah,
I did sine theta times sine theta minus sine theta times cosine squared theta sine theta. I did the distributive property. I multiplied in by the sine. And so this became sine squared, and these sines went to 1. Did that answer your question?
yes, thank you.
I just got in a hurry here and didn't write this step down. Normally I would put this step in between. And it's a good idea to show every single little step. Because if you got something different from here to here, you got something different than I thought you should have gotten. then I did, and I don't see how you got that, then I can't help you with points. Okay, if you show me this step here to show me how you got to here, and something went wrong between here and here, I could help you with points. But if I can't see how you got over to here, I can't help you with points. So where I would take off 2 or 3 points, I could probably just take 1 or 2 points off. But, and that also means you won't be able to get to this. Yeah. In my very first analysis class, on the final, he had found out that people were cheating on his first test. And so he wanted to make it really hard for those who were cheating, that they would fail miserably. And as a consequence, the rest of us had to suffer. And so on one of the questions on this test, I got to a point, couldn't figure out how to go from there to where I needed to go. And so I started working backwards. I worked from the end result. And so it's like I started from this to see where it would meet up in the middle. Well, I couldn't find out how I got from this line. I knew it was true down to here, and I knew it was true from here on down, but I couldn't see how to make the two fit. And so I wrote some gibberish in between, and professor caught that, circled it, and said, "What is this?" So I went and talked to him after the test, and he goes, "Yeah." Anyway, he was a good guy.
I have another question.
Yes.
Okay, so when you put sine squared theta minus cosine squared theta, what happened after that? I can't really see it.
Oh. On the formula chart, I know what cosine squared minus sine squared is. But I don't have something for the subtraction going the other way. All right, on the formula chart, this does not exist. So I need to change the order of the subtract. So if I divide out or factor out a -1, so I factored out a negative here. So the cosine became positive and the sine became minus. It gave me this, which is in the identities. The trig identities. And that's cosine of 2 theta. But it's the negative of cosine 2 theta. But cosine 2 theta is 2 times cosine squared theta minus 1. But I still have this negative sign out here. And so multiplying by bringing the negative sign in, the 2 cosine theta becomes minus 2 cosine theta, 2 cosine squared theta. And the -1 becomes a positive one. So it becomes 1 minus, which is what we needed. Did that help?
Yes, thank you.
Okay. I don't know if you just wanted to know from here to here, but I tend to over-explain sometimes. Okay. All right, does anyone see one that they want? Oh, cool. Trapezoid. Oh, I have to look at the trig identities to figure that one out. I'm looking at number 10. Number 10 is 1 plus tangent squared. Of u. I would use theta all the time, but they don't like doing it. 1 minus sine squared u. And they're saying this equals 1. What's 1 minus sine squared? I know what 1 minus sine squared is. What is it? Cosine squared. That's one of the ones that should be residing in your head. The sine squared plus cosine squared equals 1, or 1 minus 1 equals the other. So. And I'm going to write this tangent squared as sine squared over cosine squared. So we have 1 plus sine squared u over cosine squared u. And now, like in that other problem where I'm going to use the distributive property here, it's going to be cosine times 1, which is cosine squared u plus cosine squared u times sine squared u divided by cosine squared u. This one started out a head scratcher for me, and now it becomes so obvious to me what's going on here. The cosine squared u and the cosine squared u in this product here go to 1, so that just leaves me the sine squared here. So cosine squared u plus sine squared u, what does that equal? If you do the commutative property, it's sine squared plus cosine squared. What is cosine squared plus sine squared? What does it equal?
1.
There we go. I thought this one was going to be a little more complicated than it is. We did the trig identity, the Pythagorean identity here to get cosine squared. And here we did the quotient identity to rewrite tangent as sine squared over cosine squared. And then we just use the distributive property to get this expression here. And then we simplified this product. And then we're used to seeing this written as sine squared u plus cosine squared u, which again still equals 1. So you can go through the trouble of rewriting it that the way you're used to seeing it if you want to. I had a person one year work a particular problem, and they worked it, and they took them twice as long to get it done than it normally would because they did a full circle. They came back to the original and then continued on in a different pathway and got to where they needed to be. Everything was correct, except they went, but it's like they came from here, went, did a whole bunch of work and came back to this again, and then went a different path from there. It happens. I've done it myself. Okay. I like that one. That was nice. The ones that are have fractions in them are a little scary for people. Huh. Does anyone have that, the trig identities worksheet where the problems pulled up? You have one you want me to look at? Some of these look really interesting.
Can you do number 29?
Oh, I was just looking at 30. Okay, 29. Ooh. I'm thinking number 29 uses a formula for factoring the difference of two cubes. I changed their V to a theta. I'm going to keep it what they have. One plus sine cosine. Number 29. Oh, it is in theta. I looked at a different problem. Sorry.
At the bottom.
The bottom is different than what I wrote. It says sine minus cosine. Okay, so you can see I looked at a different problem. Okay. Sine minus cosine, right?
Mhm.
And what's it gonna equal? 1 plus sine cosine? Yeah, we're gonna use something that y'all have seen maybe once or twice. A cubed minus B cubed equals A minus B times A squared plus AB plus B squared. Oh, that just falls right out. And the sum formula, it looks exactly the same except for if it's plus between the two, then the binomial has a plus sign. If it's minus, then it's a minus between. And then the first sign in the expression is the opposite sign. Please look for patterns. So this sine cube minus cosine cube follows this pattern. So we're going to have sine theta minus cosine theta. You take the cube root of each of the cubes and you subtract them. And you're gonna multiply by the first one squared, sine squared. And it's gonna be plus the product of the two, sine theta, cosine theta. And then you're gonna add the square of the second term, plus cosine squared. Okay. And all of this is being divided by sine theta times cosine theta. So I was gonna write something else. Cosine. No, it was minus, right? Minus, it's right in front of your eyes, Thomas. Sine theta minus cosine theta. Well, here I'm subtracting sine and cosine in both the numerator and denominator, so those go to 1. So all I'm left with is the expression sine squared theta plus sine theta cosine theta. Sorry, I'm starting to write small. Plus cosine squared theta. Well, boom, I've got the sine cosine theta of theta. So now I need to make sine squared and cosine squared equal to 1. Well, guess what? They do, don't they? So I have sine squared plus cosine squared, which is 1. And then I'm just adding the sine theta cosine.
And if they're separated, you can still do it.
Well, can't I do the commutative property and switch my adds around? And I can rewrite this as sine squared theta plus cosine squared theta plus sine theta cosine theta? Can't I
So-
do that?
In the test, would you like us to write it like a second one, or does it matter if they write it like the first line one?
You can have this line in there or not, it doesn't matter. Because what you're doing, you're combining these two to get 1.
Oh, so it's kind of like if you combine like terms.
Right, you're combining like terms. You can move things around, and then you can use the associative property to tie these together, so I can add these separate from that. When all you're doing is adding, you can add them in any order you want to add them. When I add a row of numbers, I look to see what numbers add to 10 first, and I take those out. And then I manipulate the rest so I get 10s plus something else. And what is that? Core math? Is that what it was called? It was illegal to teach it in the state of Texas. Texas is so stupid. Like I can say 8 plus 5 is 8 plus 2 plus 5 plus 3. Sorry. Or I could say it is 3 plus 5 plus 5. So here I have 10. Here I have 10. 10 plus 3 is 13. That's how core math works. You're taking numbers apart and that's what I say, right? We take things apart and put them back together again. Well, we take them apart so we can put them back together again in an easy way. Adding 10s is easy. Anyway, I don't know everything in core mathematics, but that was one of the big things people harped about is, well, how can you do that? Why do that? Well, because it makes easier numbers to add. And a lot of these you can do in your head. So you don't necessarily need to memorize that 8 plus 5 is 13. You just know that, I borrowed 2 from the 5 to leave 3, so 8 plus 2 is 10, so that's going to be 13. Or I borrow 5 from the 8 to add to 5 to make 10, and that leaves a 3 to add to 10. Okay. That's how I do a lot of my adding in my head. I use that process. And it's, I think of the threes, these threes as the leftovers. And so then I go through and I look at the leftovers to see which ones add to 10, either in pairs or triplets, or like I have a 1, a 4, a 3, and a 2. Those will add up to 10. The digits 1 through 4 add to 10. That's cool, isn't it? And there's a formula for adding numbers that are in order, like 1 through 20. I add 1 through 20 together. That's wait a second. 1 through 20. That's 210. Oh, Mr. Reed, how'd you do that so fast? Well, I won't do that here. If we get into series and sequences, we do that. But I don't know if we're going to be able to this semester. Any other problem?
What about number 33? I don't think I've ever seen that, or it's just like not coming in my head.
Ooh, they threw a natural log. Natural log of the absolute value of cotangent. Cotangent what? U? We should have quit doing that. U, okay. So the reason they threw in the absolute value is because you can't take the natural log of a negative number. Okay. It doesn't exist. It's not in its domain. The domain of natural log is everything greater than 0, all positive real numbers, not even including 0. Well, cotangent I can write as cosine over sine. Well, one of the properties, we have the quotient property of logarithms, where if you're taking the logarithm of a quotient, then it's going to be the difference of the logarithms of the numerator and denominator. So I'm going to take the logarithm of the numerator, which is the cosine of u, and I still have to do the absolute value on it, and I'm going to subtract the natural log of the sine, the absolute value of the sine of u. What were we trying to get to? That. Once we rewrote cotangent as cosine over sine, then we just used one of the properties of natural log. And yes, I'd be well within my rights to throw that at you, but I shall not. Unless you're forewarned and forearmed. Number 34 uses the product property of logarithms. If let me see how it's written is, if you have the log of a product, then it's going to be the log of the, it's going to be the sum of the log of the factors. Or if you have the sum of 2 logs in the same base, then you can write it as a single log of the product of the 2 arguments. So that's how this one is done.
And then if it's negative, it's obviously like nothing, right?
Hmm?
If it's negative, then like we can't really do anything.
Right, and the stipulation here is that m is greater than 0 and n is greater than 0. The graph of logarithm, if you recall from college algebra, goes like that. Where the y-axis is a vertical asymptote.
So if it's like dividing, that means that it's subtracting and then if it's multiplying, it's adding?
Right.
Okay,
Addition is multiplication is repeated addition. Division is repeated subtraction. And natural logarithms, logarithms deal with logarithms are exponents. So this would be an exponent that I put on the base that equals this number. So the base of natural log is e. So e to whatever number this is, the natural log of the absolute value of the cotangent of u, this is going to equal the cotangent of u. Well, no, it won't even have to be, well, it would have to be positive. I don't know if we would need the absolute value symbols in this case. But maybe we do. I think there's a little bit more involved with that, but. Okay. Now, exponents can be positive or negative. So although I can't use a negative number here, I can get negative numbers. And I can't use 0 in here, but I can get 0. Okay. Down further. Usually get harder the further down you go. I want to do number 50 just because I think it's interesting. And I'm kind of playing with how to do it in my head already. Sine cubed. Sine cubed theta times. Is it cosine squared?
Yeah.
And it's going to equal sine theta times cosine squared minus cosine to the 4th. Oh, minus, right?
Minus.
First thing I would think to do is to factor out the sine. Factor out a single sine and say it's sine times sine squared theta cosine squared theta. And
What number is this?
number
50, you said?
50. So using the Pythagorean theorem here, I mean, the Pythagorean identity on the sine squared, because all I want is cosine in here. So I'm gonna rewrite sine squared as cosine. And so that's gonna be 1 minus cosine squared theta times the cosine squared theta inside here. And we still have the sine theta on the outside. And now I just do the distributive property with the cosine squared. So I have sine theta times the cosine squared theta, cosine times 1, minus the cosine squared times cosine squared, which is a cosine to the 4th theta. So this looks scarier than it actually was. You just factor out the sine because I know stuff about sine squared and cosine squared. I don't know much about sine cubed. So I throw that to the outside. It needs to be to the outside anyway. And then over here, it's only in cosine, so I'm going to rewrite sine in terms of cosine. And then simplify by multiplying in by doing the distributive property. And we'd be done. I'm picking these ones that I think are scary and they're not. I came across one time that took about half the board to work through. I kept making mistakes. Students kept pointing out I could do this and I could do that. And we eventually got to the correct pathway. Or one correct pathway. And then I looked it up to see how they did it. And where I did about 10 to 15 transformations. They did 3 or 4. So you'll eventually get there. It's just it may not be the most efficient way, which is fine, as long as each move is correct. And it moves you forward towards your goal. There may have been a few steps in there that were cyclical, which means they came back on themselves. But I don't know where to remember. It was a long time ago.
I have a question before you exit.
Yeah,
You factored out the sine
yeah.
on the left side or both sides?
No, just this is what they gave me. All right, they had a single sine by itself. Well, I can do that real quick. Just by factoring this to sine theta times sine squared. So I didn't even need the parentheses here. Okay, I could have just written it this way. But I put parentheses here to tell me that I'm going to leave the sign out here. And everything else is going to happen inside the parentheses. So I want inside the parentheses to end up looking like that.
So what happened to inside the parentheses? Because I can't really see.
Okay. I use this Pythagorean identity. I rewrote sine as 1 minus cosine squared theta. And then we're still multiplying by the cosine squared. And so I multiply cosine squared times 1 and cosine squared times cosine squared, which would give me this here.
Oh, okay, I see. Thank you.
Okay.
I don't know how your brain thinks of that. I'm like,
Say again?
I said, I don't know how your brain thinks of that. I probably wouldn't have thought of doing it like that.
Well, you know, I have a lot of those formulas already in my head. Okay, so in my head, I can write sine squared in a lot of different ways. And one of the ways is to write it this way, using the Pythagorean identities. And that's why, please print that formula chart out. All right. If you do not have the capabilities, find someone who does and see if they'll print it out for you. Or come to school and I don't know, how much does it cost to print stuff out at the school?
I'm not sure.
I don't know. It's not very much. When I was in school, it was like $0.10 per page. And if you went after so many pages, the cost went down a little bit, but. I don't know, if you go into the library, I think the first page is free, I guess, I don't know, you get some free. That's all I know. So print those out, because you can use them. Okay. You can use it on the exam. What else?
Can we do the 56?
56. Ah. That's an ugly one, isn't it? Here's the problem with a lot of trig identities. You want to use only trig identities and to see how those things play out. Sometimes you have to use some algebra techniques, like factoring. Five cosecant squared, what are they using for theta? Using x. Plus 4 cosecant x minus 1 being divided by something squared, right? Cotangent squared. Well, cotangent squared is it 1 minus or something? It's cosecant minus. Oh. Okay. They want it to equal. Here we have cosecant x in the denominator minus 1. Sorry. And 5 cosecant x. Is it minus 1 again? In the numerator? Oh, I see that now. Yeah, I can rewrite cotangent. I can rewrite cotangent as, isn't that cosecant squared minus 1 in the trig identities? Because I want everything in cosecant on my end, so I want to rewrite cotangent as cosecant.
Yeah, that's
So, okay. And if I think of cosecant x as u, then this becomes 5u squared plus 4u minus 1. Well, that's a quadratic I can factor. And the hint is, I bet this is one of the factors. 5 cosecant x minus 1. So all I need to do is find out what's over here. Well, to get cosecant squared, 5 cosecant squared, all I have to do is multiply this by cosecant x. Keep wanting to write cosine. Fucking hell, Thomas. And then I know we have the factors of 1 to get this number here. But to get a negative 1 there, I have to multiply by a positive 1. Right? And to make sure I did it right, I make sure that my middle term works out to be the same. So 5 cosecant times 1 is 5 cosecant x, and then negative 1 times cosecant x is a negative cosecant x. When I combine them, I get 4 cosecant x, which is what I needed to get. So I just did this work to verify that I factored correctly. And this is the difference of 2 squares. I forgot the x there. This is u squared minus 1, right? If I follow this thing here, well, this factors nicely to u plus 1 times u minus 1. So now my denominator is now cosecant x plus 1 times cosecant x minus 1. My numerator is 5 cosecant x minus 1 times cosecant x plus 1. Does everyone understand how I got where I got? The trig identities isn't going to work here totally. The only place we're really using the trig identity is changing the denominator to something else. And now we're just factoring. Everything else is factoring. We factored the numerator, factored the denominator, and now we look for our ones. Right, a factor that's the same numerator and denominator. These are the same, cosecant x plus 1 and cosecant x plus 1. Those go to 1, so we're taking out our ones. And so what's left is the 5 cosecant x minus 1 in the numerator and the cosecant x minus 1 in the denominator, which is what we needed to get to. The trick in this one is to recognize that you can factor the denominator. I mean, you can factor the numerator. So if I can factor the numerator, I can rewrite my denominator into something I can factor. Right, the trig identities give you things that you can factor as the difference of two squares. 1 minus sine squared equals 1 minus sine of theta times 1 plus sine of theta. So you can factor it. And with doing trig identities, that comes helpful. So we used one trig identity and the rest of it was algebra. If you understand this and you can do this and you can see how it applies to some of the other problems, you will not have a problem on the exam because I'm not going to necessarily throw something that's going to require this kind of manipulation. So I'm toying with the idea of giving a whole bunch of simple ones to do, which takes 2 or 3 steps to get to the end. Or fewer, slightly more complicated ones, where it's going to take what this was 1, 2, this took 3 steps. But it had you thinking out of the box a little bit because you had to go into your algebras. Well, whatever led up to this course is free game to use in this course. That's why I threw the natural log stuff on there. Number 57 is just like number 50. Only it's easier. You factor out cotangent, and then cotangents, well, not everybody has that up. So it's cotangent cubed theta equals, I don't know if they use theta or not. Once I factor cotangent out of this, so I have cotangent on the outside, cotangent squared, and we use that trig identity here. 1 minus cosecant squared. 1 minus cosecant, oh, I forgot to write the theta there. 1 minus cosecant squared. I mean, cosecant squared minus 1, sorry. Said it the wrong way. So that's just a matter of writing this as cotangent theta times cotangent squared theta, and then you get the cotangent theta times the cosecant theta minus 1. Cosecant squared minus 1. So that one was just a 2-step process. Using factoring from algebra, because 3 cubed is 3 times 3 squared. That's all we did there. Okay. Let me see. So let's look at number 18. And that's the last one we'll do today. One minus secant. Divided by tangent. Plus the reciprocal. Equals 2 cosecant, negative 2 cosecant, okay. Well, one thing to do is to write this as a single fraction. The common denominator is going to be multiplying these two together. So that means this fraction here gets multiplied by 1 minus secant divided by 1 minus secant. And this fraction over here gets multiplied by tangent over tangent. Right, so that way these two denominators become tangent of theta times 1 minus secant of theta. Now the numerator, I end up with 1 minus secant theta being squared plus tangent squared. Well, 1 minus secant squared, you square that. So that gives you 1 minus 2 secant plus secant squared theta plus tangent theta, tangent squared theta. All right, I'm adding that in there, and down below I still have the tangent of theta times 1 minus the secant of theta. I want to end up getting cosecant. So how do we do that? What is tangent squared equals? What's the Pythagorean identity for tangent squared? I don't have that one in my head. What is it? Is it secant squared?
Tangent squared of theta equals secant squared minus 1.
So we have 1 minus 2 secant theta plus secant squared theta plus secant squared theta minus 1 over tangent squared, just tangent theta times 1 minus secant. So here I have 1 minus 1, those go away. And then I can combine these two. Write it down over here. And so now in the numerator, I have 2 times a negative 2 times secant theta plus 2 secant squared theta divided by tangent theta times 1 minus secant theta. Well, I'm gonna change the order here. Do I want to change the order? No, I'm gonna keep that order the same, because I'm gonna need a factor of -2. So if I divide -2 out of both of these, if I divide a -2 secant out of both of those, so I have a -2 secant theta. So that gives me a +1 here. And dividing 2 secant out of this just leaves me secant. But dividing negative makes this become minus secant theta over tangent theta 1 minus secant theta, right? In my head, I'm thinking I need to get 1 minus secant theta in the numerator so I can get rid of it. And at this point, I start seeing it. Because I can combine these two to get this one, and then when I divide a -2 secant out of both of them, I'm left with 1 minus secant theta. So now I have a factor that's the same in the numerator with a factor in the denominator, and so those go to 1, and so I'm left with, and I'm going to bring the -2 to the outside, -2 times secant theta divided by tangent theta. Well, I'm going to rewrite secant and tangent in terms of sine and cosine. So this becomes a -2 of 1 over cosine theta being divided by sine over cosine. And dividing by a fraction is multiplying by its reciprocal. So this is going to be 1 over cosine theta times cosine theta over sine theta. And I'm showing more steps than they do, I think. And the cosine over cosine is 1, so those go away because they go to 1. So now we have a -2 times 1 over sine, which is a -2 times cosecant, which is what we needed to get to. The difficulty here is to see where is it going to lead you to. I did not see where it was gonna, once I got to this point, I knew I had to square this. And then I knew I could rewrite tangent as secant. And then I realized that the ones will disappear and that becomes 2 secant. And that helps me get the 1 minus secant in the numerator, so I can take out the 1 in the denominator away from it. And so that just left me a -2 secant over tangent. And I pulled the -2 out because that was going to have to stay. I knew I was going to have a -2 at the end. So I pulled it out and left it out of the rest of the calculations other than keeping it in out front. And then one of the first things they tell you to solve these things is see if you can write everything as in sines or cosines. So I can write these in terms of sines and cosine. And so I'm dividing a fraction by a fraction, which I change it to a fraction being multiplied by the reciprocal of the fraction it was being divided by. A lot of words just to say you flip and multiply. And then we use the reciprocal identity to get the cosecant that we needed. It's not hard. It's complicated, yes. And that's why a lot of people think it's hard. But it really isn't. It's just looking to see where do you need to go from here? How can I use this to get to there? How can I change it so I can combine things or take them apart again to simplify it so I can get there? So that's all we were doing here. Yeah, we made it more complicated. This is much more complicated than just adding the two fractions. But the next step made it simpler, because now it became easy to solve. Well, in my head, anyway. A big problem people have is seeing that you can factor out a negative to make it look like you need it to look. Okay, it needed to be 1 secant minus secant squared, not secant, a negative secant plus secant squared. And so you divide out the negative, then you get what you needed. Now I could have done this in 2 steps and just factored out the -2 first. And that would have left me secant theta minus secant squared theta. And then from here, I could factor out that secant. So I wind up with 1 minus secant in the numerator that I can take away with the 1 in the denominator because they equal 1. God, this is fun. How we going to share history? You're insane. Okay. My wife's been saying that for a long time. Did I mention that she thinks I do the devil's work? And so we are thinking, yeah, you are. Okay. Unless y'all have questions for me, I'm done with y'all for today. And I will see you on Monday. No, not Monday. What's today? Today's Wednesday? Yes, I'll see you on Monday.
What time is it?
Right now, it is 9:43. No, 9:38. 9:38.
My phone died, so I just need to know the time.
9:37.
Thank you.
Coming up to 9:38. Okay.
Bye. Thank you. Have a good day.
You too.
You have a good day. Take care.
You too.